Hello, and welcome back to our course on Descriptive Data Analysis. In this class, we are going to study frequency distribution and contingency tables. The frequency distribution is a listing that specifies all possible values or categories or intervals of a given variable and quantifies its frequency, that is, its occurrence. The goal of the frequency distribution is to quantify the occurrence of the different values of a given variable. And they can be visualized either using a frequency table or using a specific type of graph called a histogram. We have three main types of frequency distribution. We can work with the absolute frequency of a variable. This corresponds to the count of each possible value, interval, or category of a variable. We can work with the relative frequency, which is the frequency in relation to the total number of objects that we have. Here we can talk about objects or observations. And the cumulative frequency is obtained by adding all the current frequency values with its predecessor value. And so you accumulate the frequency values over the possible values. To illustrate, let's take the case of the mammographic dataset. This dataset is available at the University of California at Irvine Data Repository. The link is here in case you want to download the data. This dataset is about mammographic exams. In these exams, they take some specific measures of a mass that is captured within the image exam. First variable that we have here is the BI-RADS. This is a score that is given by the radiologist. Then we have the patient's age and the three variables associated with the mass visualized in the exam: the shape, its margin, and its density. And finally, we have our target or goal variable, which is the severity level obtained by the exam. And the severity level can be either malign or benign. The first thing that we are going to do here in terms of calculating the frequency distribution is we are going to take the variable shape, the shape of the mass that's observed in the exam. And this shape can assume 5 different values. It can be irregular, round, oval, globular, and this last value here indicates that there is a missing value there. The first column shows us the absolute frequency of each of these possible values of the variable shape. And this means that we have 400 patients with a mass whose shape is irregular, 224 patients with a shape of round form, 211 patients of oval shape, 95 patients with globular shape, and we have 31 missing values for the variable shape. To calculate the relative frequency, all we need to do is to take the absolute frequency and to divide this value by the sum of all values that we have here. And this means that the relative frequency is the percentage that this category, irregular, has in relation to all the others. And as we can see, we have 41.62% of the patients presenting an irregular shape. The cumulative frequency takes the same values. Here we are calculating the relative cumulative frequency, but we could also calculate the absolute cumulative frequency. In this case, to calculate the cumulative frequency, all that we have to do is to sum the current value of the frequency with its previous ones. So this value here is going to be this current value, which is 23.31 plus 41.62. The total is 64.93. Then I sum this with the previous two. I get 86.89. I sum this with this previous three. I get 96.77. When I sum this with all the previous one, I have 100%. On the right hand side, we've got a pie chart. This pie chart is showing the percentage now as slices of a chart. To move on with our explanation, let's now present the forest fires dataset. This is another dataset available at UCI. The link is here for you to download. This dataset is about some forest fire in a park called Montezinho Park in Portugal. Here we have the coordinates, and these are the coordinates of the areas delimited by the study that was performed. We have the month and the day, in which these measurements were taken. We have some specific variables which are FFMC, DMC, and DC. These variables are related with some specific moisture code or drought code that they were assessing in that region. We also have the initial spread index of the fire, the current temperature, the relative humidity, the wind, the rain, and the area that was affected by the fire. This dataset contains a total of 517 objects and 13 variables. Now, let's have a look at the frequency distribution of the variable temperature. To plot the frequency distribution of the variable temperature, we use a graph called histogram, and what the histogram does is it divides the range of the variable into a predefined number of bins. In this case, we chose to work with 10 bins, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bins, and they are of same width. This means that the width of this bin is the same of this one and all the other ones. And what we have to do now is to calculate the number of objects that fall within each one of these bins. After you do that, this number will be represented here by the height of the bin. By looking at the table, we have the bins here. This is an open interval on the value 0, and it's closed on 3.33. It's open on 3.33 and closed on 6.66, so on and so forth, until the last value, which is 33.3. Here we have the absolute frequency, and this means the number of objects that fall in each of these bins. And as we can observe, in the first bin we have a single object, and this is very much probably an anomaly or an outlier because its frequency of occurrence is so much smaller than all the other bins that it can be considered an anomaly. Then we have the relative frequency and the cumulative frequency, which we have already studied. Now that we have seen the practical application of the frequency distribution in the histogram, let's have a look at some concepts. The histogram can be defined as a visualization technique that allows us to explore the pattern of a single variable distribution, and this is something very important. Histograms work on a single variable. The x-axis represents the range of values, whilst the y-axis represents the absolute or relative frequency of data points within each bin. Histograms are very important because they allow us to explore, for example, the central tendency measures that we are going to see in our next class. And also it allows us to observe dispersion measures. It allows us to see the number of modes or the number of peaks that the distribution presents. It allows us to observe, for example, the presence of outliers and also the skewness of the distribution. Let's explore some other important concepts that we have when working with histogram. The first concept is the concept of a mode. A mode is in essence a peak that we observe in the histogram. So when we look at this histogram here of the variable month, we can see that we have one peak here in the month of March, then we have another peak here combining the months of August and September, another peak here in the month of July, and another peak in the month of December. This means that we have 4 peaks here, and so this distribution is called a multimodal distribution. What we are also showing in this picture is this smooth curve over the histogram, and this smooth curve is a type of density curve that is plotted based on an approximation, assuming that we have an infinite number of points here, of the real distribution of the data. Because the histogram discretizes the data into some intervals so that we can observe the frequency of occurrence in each interval or bin. Another thing that we can observe with the histogram and the frequency distribution is the presence or absence of tails. In the case of this curve, this is the frequency distribution for variable FFMC. We can see there is a long left tail. This is a left tail or a negative tail. And this means that we have some values that are here, but they appear in a very low frequency when compared with the values that are, for example, here closer to the mean and median of this distribution. This long tail shows that we have some outliers in this variable. Here we have the frequency distributions for other variables, like the month that we've seen before and the day. In the case of the day, we can observe three modes. So this is a trimodal or a multimodal distribution. But this is also an almost uniform distribution. And this one doesn't have a tail as long as the tail that we saw in variable FFMC, but it also has a tail, in this case to the right, or a positive tail. Again, we have variable FFMC and we have variable DMC with a short right tail. To conclude this class, we are going to discuss about contingency tables. The goal of the contingency table is to summarize the relationship between categorical variables. If you don't know what's a categorical variable, please visit our series on data description, because there we are going to describe different types of data and how to categorize them. To illustrate a contingency table, let's take again the case of the variable shape of the mammographic dataset. We've seen that shape can assume 4 possible values, and here I am disregarding the missing values. And what we have here is our target variable, which is severity, divided into benign or malignant. And the contingency table is presenting to us the frequency distribution of each possible value of the variable shape in relation to each of the possible values of our target variable. The way that we read this table is we have 158 patients with a mass of shape round of the type benign, and we have 32 patients with a mass of shape round and of type malignant. And this type of table is important because, as we can see here, if the shape is round, in most cases the severity is benign. By contrast, if we look at the frequency distribution of shape irregular, we see that in most cases that the shape of the mass is irregular, we have a malignant severity for that patient. Thank you for watching this class, and see you in our next class.